Hello and welcome back to PC Retro Programmer. In today's video we're going to continue our quest to get a linearly addressed graphics mode in CGA, albeit not a particularly practical one. And at the end of the previous video I left you with a little bit of a puzzler. We'd set up a kind of mode with one scanline per character and 200 scanlines displayed, and everything seemed to be going okay until we changed the number of characters displayed in the horizontal direction. We changed that from 40 down to 32, and all of a sudden the display lost sync. So we're going to start off today by taking a look at that code again to see what actually went wrong. And don't beat yourself up too much if you didn't manage to figure it out. In fact, in today's video I'm going to show you an even more obscure issue, although I won't leave it as a puzzler for next time. I'll actually show you the resolution today. Now, as to our first guess of what might have caused the loss of sync in the previous video, we might suspect these register updates here. We've got 4 CRTC register updates that happen in the active portion of the first scan line, and then we immediately jump down to skip first, and you can see there's another one. So there are 5 that have to occur in the active region before we start polling for the non-active region. And this is a reasonable guess given that we have reduced the active region from 40 characters displayed down to 32 characters displayed, so maybe we're just running out of time to do all our register updates. It's even worse than that because the polling for the start of the active region is pretty slow. I didn't work it out exactly, but it's something like 25 cycles per iteration. And if we just miss the start of the active region on one iteration, then it's another 25 cycles before we have another go, and then this means we could be almost 25 cycles into the active region before we even detect it. Now, the entire raster line is only 304 CPU cycles, and obviously the active region is just over half of that. So we really don't have a whole load of time altogether in the active region of each scan line. But this isn't actually the issue. The worst thing that could happen here is those 5 register writes could take a little bit longer than the active region, and we'd be some way into the non-active region before we started trying to poll for it. The first iteration would immediately succeed and say, yep, we're in the non-active region, and things would just continue on exactly as they did in the previous version. So it really doesn't matter too much that we took a little bit longer. If we had code in the non-active region as well, and there now wasn't time for that, then it could actually propagate and cause an issue. But that is not the resolution of the problem. It was certainly my first guess, and it's a reasonable guess. It just doesn't happen to be correct in this case. Our problem is actually caused by code at the end of our CRT loop. This final loop deals with the last 102 scan lines that actually display pixels. That's 98 through 199, and once those are done, we should in theory be in vertical blank. And it's there that we change these 2 values, vertical total and displayed, to 127. Now, these were previously set to values deliberately that the CRTC doesn't actually reach in order to trick it to wrap around when it gets to the maximum value it can actually count to, which is 127. It goes one beyond that, which wraps it around to 0 and keeps counting up from there to whatever values you put in the registers. So we, somewhere above, put 72 in vertical displayed, which gives us an effective vertical displayed of 128 plus 72, which is 200. And that's exactly what we want. And at that point, we're then ready to change vertical displayed back to some large value, 127, for the start of the next frame. And likewise, somewhere above, we set vertical total to 87, sometime after it had already passed that point, and this tricks it to wrap around at the 127 back to 0 and start counting up again back towards the 87. But before we get there, at this point precisely, we change the value again to 127, and so actually on the second time around it also counts to 127 plus 1. Remember, it always counts one more than the value you put in vertical total. And so that means that effectively we have vertical total of 256, which is also what we want. Now the problem that we're having is that sometimes vertical displayed is actually being changed too early. Occasionally it happens while we're still on scanline 199, the final scanline this loop is supposed to handle, and also the final scanline of the 72 that is supposed to be displayed after the CRTC wraparound. You can see that we're waiting for the start of scanline 199 and also the start of the non-active portion of 199, but we're not waiting for the end of 199. And so this loop falls through and these commands get executed sometimes while we're still on scanline 199. That's bad because vertical displayed then gets changed to 127 when it's still supposed to be 72. We need to wait till after those 72 scan lines before we change this value. And so that means we need to detect the end of scanline 199. Now, normally we'd do that by waiting for the active portion of the next scanline, 200. But we can't do that here. 200 is in the vertical blank region. It doesn't display any pixels, and so it doesn't have any active region to poll for. So what we're going to do instead is to stick a little delay in here, just enough to ensure that we're not on scanline 199 when we do these updates. It's not too critical. Vertical total is actually pretty flexible. We've already hit the wraparound ages ago, and pretty much any time after that, vertical total can be updated. And so long as we do it before it reaches the 87 that it's currently set to, everything will be fine. And we're nowhere near that. We've only just passed 72 scan lines after the wraparound. So you might wonder, why was this only a problem for us when we had 32 characters displayed in the horizontal direction and not when we had 40? Well, of course, in the 32 case, we had a much narrower active region and therefore a much wider non-active region on scanline 199. So there was actually plenty of time left on 199 for all of this code to execute and convince the CRTC that instead of stopping at 72 displayed scan lines in the current frame, it should keep going to 127, which was what was causing our loss of sync. So let's go ahead and add a delay in here to prevent that from happening. Now I'm going to be running this on a genuine PCXT, and one convenient way of getting a delay there is to use a shift with a high shift count. Now this won't work on a 286 or later because the shift count is actually masked at 5 bits, but on the 8086 and 8088 it just keeps shifting for as many bits as you tell it. So what I'm going to do is use a shift count of 100, and it'll essentially take about 4 cycles per bit that I shift, and so this is going to give me a delay of about 400 cycles if I shift AX left by the count in CL. Now each scan line on the screen is 304 CPU cycles, and so this is going to give me a delay just over 1 scan line. So I'll either be in scan line 200 or perhaps even 201 when this finishes, and that's certainly going to be adequate. Now there are other ways of doing this. You could use a multiplication instruction, for example, but I don't really care about portability here. This entire project is going to be very timing sensitive, and so it doesn't matter too much how we do this. So let's assemble this, and we'll run it on some genuine hardware to see if it's now actually performing the way we expect. Of course, I still have the code uncommented that sets horizontal display to 32, so let's see if we now have any loss of sync. And if you'll excuse the rubbish looking moire pattern, which is impossible to completely remove, it looks like it's working perfectly now. So that seems to have been the problem. Well, now that we have that resolved, we can return to our project of getting a linearly addressed mode, and it's time that we tried to force the CRTC to start pulling data from the second bank. Now, naively, you might think that we can actually get one scan line from the second bank for free around about the point where the banks cross over from bank 0 to bank 1. On the final scan line that's taken from the first bank, we could temporarily set the number of scan lines per character to 2 again, and that would automatically mean that the next scan line would be taken from the second bank. The only problem is the data isn't taken from the beginning of the second bank, it's taken from the end of the second bank, because it's the scan line pair of the one that we just displayed, which was at the end of the first bank. So somehow or other we need to induce the CRTC to start taking data from the beginning of the first bank again, so that when we get data from the second bank, we're actually taking data from the beginning of the second bank. So the way that we're going to do this is just to put a small scan line with row address 0 in the right hand side of the screen in that blank region at the end of that final scan line that's taken from the first bank. So this will convince the CRTC that it should be taking data from the next location in the first bank, which will cause it to wrap around to 0, and then when we pull data from the second bank, we'll get data from the beginning of the second bank. So that's what we're going to try first. We're going to pull some scan lines out of our loops just so we can work on them individually and experiment, and we're going to try and get one scan line of data from the second bank, but we want it to be taken from the first part of the second bank. Let's take a look at the next iteration of code that I've written for all of this in linear8.asm. And the first change that I made was to make the first line of the second bank a different color so that we can tell for sure when we're getting data from there. So it's now going to be white, black, and so on, instead of magenta, black for all the other lines. And the temptation I had was to make that 80 bytes, but we're actually only dealing with 32 characters displayed in the horizontal direction now, which corresponds to 64 bytes. And the other temptation I had was to think of the crossover between the two banks as being halfway down the screen after 100 scan lines. But this is not correct either. There's actually 128 scan lines of 32 characters in the first bank, and so this is about 2/3 of the way down the screen. The next thing that I've done is to pull some scan lines out of the loops that we had previously so that we can deal with them separately. So we previously had a big long loop all the way to the end of the frame, and it now stops at scan line 126, and I've pulled 127 and a few of the following scan lines out separately. Now from this point on, I'm actually going to stop referring to them as scan lines and start referring to them as raster lines. So the convention is that a raster line is a line on the monitor, and in our case we're actually going to have multiple CRTC scan lines per monitor raster line. So it's going to get a little bit annoying to start referring to these as CRT scan lines and CRTC scan lines. So I'm going to use the convention that a raster line is a line on the physical display, and a scan line is now just going to refer to a CRTC scan line, which could be any size. It could be very small. Now, raster line 127 is the final one where we want data to be taken from the first bank. From raster line 128 and following, we want data to come from the second bank. Now, as I explained above, this means that we have to break raster line 127 into two shorter scan lines. The first of those will actually display the pixels from the end of that first bank, and the second of them will be blank. It'll be to the right of that first one, and it's where we're going to set row address 0, and we'll set the number of scan lines per character to 2, so that the data on raster line 128 comes from row address 1, which will mean the second bank. So this is done by setting registers, and I'm going to set the total width of that first scan line of raster line 127 to 33. And remember, we always put one less in the horizontal total register, so it'll be 32. And the second scan line, I'm going to have a length of 24, and you'll see that down here. And of course, I put 23 in the horizontal total register. Now, those horizontal total registers should take effect immediately. So whatever it was set to before, so long as we're below that value that we're setting it to, it'll just count up to that. So it should count to 32 plus 1. Now we've got horizontal total set to 32, and horizontal displayed is also currently set to 32, but it turns out the Hitachi CRTC that's in my IBM graphics card automatically blanks the final character of every scan line. Now, we don't normally see that because it's happening in the border region, but it does happen nonetheless, and it's actually going to be relevant for us, as you'll see a little bit later on. But the idea is it'll display 32 characters, then one blank one. That'll give us 33, and then we're done with that first scan line. Now, in the second scan line, I don't want any characters displayed, and so I want the horizontal displayed to be 0. But I can't wait until I'm already on the second scan line to set that. I'll have already displayed some pixels at that point, so I actually need to set that before I get there. And so, in fact, I have to set it while we're still on this first scan line. And so long as I'm setting that to a value that's lower than the position that we're currently up to, which is certainly the case here, then it'll just keep going until it reaches that value, which it never will in this case. And so what we should see is the 32 displayed characters plus the one blank one that the Hitachi CRTC puts in. And then the value for horizontal displayed is already set in time for the next scan line, which is what we want. Now the other thing I need to worry about is the horizontal sync pulses. They normally happen at 45, and in this particular case 45 would be beyond the end of this first scan line, so we need to put the horizontal sync pulse for the correct position within the second scan line on this raster line. And so that is position 12, and it makes sense to also set that in advance just in case we miss it. There shouldn't be any harm in doing that, so long as we wait until we're already past 12, because after all, we don't want a second sync pulse on this raster line within this first scan line. So in order to make sure that I'm definitely past 12, I just put a small delay in here, and I just experimented with this, and 10 no-ops seems to do the job plenty good. So this is just a little macro feature of Turbo Assembler. If I do rept10, it'll just repeat the following code 10 times, saves me writing 10 lines with no-op on it, until I reach the endm or end macro directive. So that's the end of that first scan line, and of course once we reach that, we should be in the non-active region. Things should go blank, in fact, from the final character of this scan line onwards. And so now we should effectively be in the second scan line. And as I said, we're going to set the horizontal total for this to 23. I'll also set the number of scan lines per character to 2, which means setting the max character scan line value to 1. And this means that this second scan line on the raster line will have row address 0, but the next one will have row address 1, which is what we want. That'll pull the data from the second bank when we're on raster line 128. And I'll also set the horizontal displayed back to 32, since I definitely won't have time to do that on the following scan line. At the moment, horizontal displayed should be set to 0, and so I would have 0 time to set it on the next scan line. In fact, there wouldn't even be an active region on that scan line in that case. So this really is critical that it gets done while we're still on this second scan line of raster line 127. And now we're ready to do raster line 128, which is where we should, for the first time, get data from the second bank. Well, what about raster line 128? Well, hopefully we now have row address 1 so that data is coming from the second bank for this raster line. But we just want this particular raster line to do that. From here on in, we want everything else to go back to business as normal. And so we're going to set the horizontal total back to 56, which is what it normally is. We'll set the horizontal sync back to 45, which is what it normally is. And that'll actually take effect on this scan line. So this will be a full width scan line. And we'll also even set the maximum character scan line back to 0 so that we have one scan line per character for all of the remaining lines on the screen. Now, this is not going to affect the current scan line because that's already row address 1. It's already pulling data from the second bank, so it's not going to change that here. But from the next scan line on, we'll have just row address 0 for every scan line again, as we normally do. So that's basically all we're going to change here. And from then on, we're just back to detecting raster lines again. And I've actually pulled out one additional raster line here, raster line 129, and you'll see why I've done that a little bit later. All the remaining raster lines I've just put in a loop at the end, just as we had previously. So let's save this and assemble it and actually run this on the real hardware and see whether we get what we want. Well, if this works, we should get raster line 128 that's white, and all of the remaining raster lines should be cyan. And lo and behold, we get a mess. So when I first saw this, I puzzled about this for really a very long time. So let me show you what's actually going wrong. The problem is actually on raster line 128, the one that we want to be white, the one that's supposed to be taking data from the second bank because row address is 1. And what we've done here is set the maximum character scan line to 0 on this line. Now the issue there is that this is the value that the CRTC is going to count up to. And given that it's already at row address 1, this means it has to count from 1 all the way up to the maximum value that it can count to in this register, which happens to be 31, and then it'll wrap around to 0, and then it'll stop. So what this actually tells the CRTC to do is to make a character row of 32 scan lines, which is totally not what we want. So the solution here is to move this max char scan line equals 0 out of here, since row address is 1 here, and move it to the next raster line. And this will have row address 0 again, and so then it's safe to set the maximum character scan line back to 0, and it will actually continue to have just one scan line per character from this point on. So let's go ahead and do that and see what the result is. This is what linear8.asm now looks like after I've made that change. You can see I've moved that max char scan line equals 0 down to raster line 129. And about the only thing I had to worry about getting correct here was the port address. This is 03D4H for changing a register, and it has to go back to 03DAH for that polling that we're doing for the non-active region. And this is actually the most common mistake that people make, by the way, with programming the CRTC, to forget to change or to clobber the value of the port address in the DX register. And once that's done, you can see that on raster line 128, we now only have 2 register updates. That third one was moved down to 129. So let's save this and we'll assemble it again, and we'll see whether this makes any difference to the stability on the real hardware. Well, have we finally got rid of the loss of sync, and is there now a white scan line somewhere? Well, let's find out. And it looks like we've got rid of the loss of sync, which is good. We can see what's going on, but there's no white scan lines anywhere to be seen. And there's a lot of other features in this image which are quite hard to explain. We've got 2 black regions running through the image toward the top, and everything looks like it's been shifted in the vertical direction somehow. We also have this big magenta region, and I can tell you that there are 16 magenta lines there, interleaved with 16 cyan lines, and that should be a clue given what we now know. But immediately above those magenta lines, you can see one longer than normal cyan line. It has an additional 2 cyan dots on it, which represents just 1 byte of video RAM. That's only half a character, so that's a bit of a head scratcher. Then on the next scan line we have a cyan line that starts very, very far to the right, doesn't run for very long, and then we start getting this alternating magenta cyan pattern. And of course this has got to be a horizontal sync issue. The sync pulses in the wrong place, and it takes quite some time for the monitor to recover back to where everything is now on the left side of the picture again at the bottom. So there really are quite a lot of things to explain here, and sometimes when you run this code you'll even see some flickering happening in the magenta region, so a lot to explain. Now there probably still are some really stupid bugs in my code. I've already pulled out quite a few so far before I made this video. So have a think about that before the next video and let me know if you've spotted anything that's really dumb. But there are also some features of this image that I know can only be explained with additional information about the CRTC, which we'll look at more closely in the next video. I'll also look at how to diagnose what's going on here, and this is where we'll use our trick of changing the background color so we can see where things are actually happening. So that's what we're going to cover in the next video.